Hello, we are Group E, and today we will be presenting our findings for our bioprocessing lab where we produce Lactobacillus rhamnosus. Next slide, please. So I will be doing the introduction for our group. So firstly, for the background, the dairy industry is a major contributor to the Irish economy, with an estimated value of €17.6 billion, according to a study conducted by Ernst & Young in 2022. Meaning it contributes more to the economy than Irish tourism. The raw product itself is not what generates so much revenue, but rather the premium products it can be cultivated into, such as yogurts and cheeses, which can yield much higher profits, contributing to the affluence of the industry. Yogurts and cheeses are rich in essential nutrients such as vitamin D and calcium, but also contain probiotics, which help maintain a healthy balance of microflora in the gut, promoting digestion and nutrient absorption, and overall improving gut health. Lactobacillus rhamnosus is one of the most commonly used probiotics. It occurs naturally in the intestine and vagina in adults and grows well in milk. So for the objective of this experiment, is to study the performance of a batch fermentation culture over a period of 4 days. It aims to understand how bacteria cultures behave in a batch fermentation setup to evaluate its performance under controlled conditions. This process involves several steps, including the preparation of the bacteria inoculum from a culture broth, growing the inoculum overnight in shake flasks to achieve a concentration of 10 to the power of 8 cells per ml, using this inoculum to seed a batch fermentation culture, monitoring this culture for 4 days, and finally determining the performance of the culture by assessing optical density, HPLC, dry weight, and by performing a cell count. Actually, the Gantt chart. So a Gantt chart is a type of bar chart that provides a visual representation of a project schedule. It displays the start and end points of the project and lists the tasks and activities involved throughout the timeline. We utilize a Gantt chart to divide up the tasks throughout the experiment between us, which greatly helped us to not deviate from the work required. It also helped us avoid any confusion regarding which group member was completing each task. It also ensured that each group member alternated between various tasks so that one member was not left to perform the same task each time. The Gantt chart greatly helped our efficiency throughout this process and ensured that our data was consistent. And then on to Connor for materials and methods.
Thanks, Saoirse. So our first slide is about media prep and shake flask inoculation on day one. Day one was devoted to the media prep, shake flask inoc, and Gantt chart creation. The bioreactor has a maximum volume of 3.6 litres. Therefore, we use a 2 litre working volume and double the ingredient amount. The ingredients for the media are as follows. We had skimmed milk powder, yeast extract, sodium acetate, and MgSO4. These were mixed in a 2 litre deionized H2O. A magnetic stirrer and plate were used to mix the ingredients. As the mixture became thicker, we adjust the stir speed accordingly. This media is then autoclaved at 110 degrees Celsius for 10 minutes. It is important to note that a typical autoclave runs at 120 degrees Celsius for 15 minutes, but this is adjusted to avoid clumping of the media due to it containing lactose product. It has been tested and is shown to be sterile. The media is then added to the bioreactor. So for shake flask inoculation, we inoculate 2 by 100 ml MRS culture broth media shake flasks with Lactobacillus rhamnosus under aseptic conditions. These are then grown overnight and combined to the bioreactor in day 2 with adequate amount of cells, approximately 10 to the power of 8. So for bioreactor inoculation, on day 2, the bioreactor is inoculated with a 200 ml culture broth prepared from the day 1. Prior to inoculation, a sterile media without bacteria is taken for OD data analysis, as per the red arrow. The culture broth is added to the bioreactor using a syringe, aseptically with 7% ethanol sprayed on the port before and after the addition of the culture. We allow the broth to mix for approximately 5 minutes and then take the T0 sample. From the time of T0, we draw a maximum 10 ml sample from the bioreactor every hour and perform cell counts, dry cell weight, HPLC, and optical density measurements. T0 is at 10:15 a.m. And if you take a sample every hour on day 2, you can gather 8 samples. Day 3, we gather 2 samples. On day 4, we got 1 sample for an optical density measurement and visualization of the data on Excel. Temperature and agitation speed were constant. However, we measured the base addition and dissolved oxygen percentage. I would like to bring your attention to the difference in media composition. On the left is day 1 sterile media without any bacteria, and on the right is day 4 inoculated media. There is a clear distinction of color and foam formation, which David will discuss further in the results and discussion this section. So for data collection and data analysis, as there was only 2-liter working volume in the bioreactor, the sample amount was limited to a maximum of 10 mil. This influenced how we could conduct our sample analysis. As a group, we created the following sampling plan, as shown here on the left. For the dry cell weight, you wanted to measure a duplicate and use the supernatant for the HPLC sample to save on sample usage. We allocated 2 mil to the optical density reading, which was plenty due to the dilution factor, and therefore we measured in the triplicate. For the cell count, we allocated 1 mil, as it had a larger volume, a larger dilution factor, sorry, and the hemocytometer takes 10 microliter. The 5 mil of sample left over was stored on ice or in a refrigerator in the case of a repeat experiment. 1 mil from the universal tube was taken and distributed into each Eppendorf and analyzed as per label. Here we can see dry cell weight, optical density, and cell count. Determining the optical density. So using a spec, we measure the optical density of the bacteria sample culture at 600 nanometers. Deviating from the SIP, we blanked between each hourly sample with 2 mil of Dion water. We used 3 mil cuvettes, hence the 2 mil amount. We measured the first sample with a dilution factor of 1, and if it reads below 0.1 or above 0.8, we dilute accordingly with deionized water. In this experiment, we diluted T0 with 1 to 5 dilution, which increased to a 1 in 10, 1 in 20, and 1 in 30 by the final sample. We used a triplicate to gather the measurement for data analysis, as it was quick, and due to the dilution factor, the sample was not a limiting factor. As we only want to measure the bacterial cells, we deduct the sterile media reading from each hourly sample measurement. So for the bacterial cell count, we pipette 1 mil from the universal into an Eppendorf. This can be then used to perform multiple dilutions. It is best practice to count no more than 300 cells. If there is too many to count, dilute the sample further. In our case, we began with a dilution factor of 1 at T0 and finished T25 at 1 in 20. Once diluted down, pipette 8 microliters onto the designated areas A and B on the hemocytometer. Leave the cells to rest for 5 minutes before count them. Count the cells in the top left, top right, bottom left, and the middle of the square. Add these up and then use the equation to gather cells per mil. The equation is here above the where you count the cells. This is one of the tests that took a longer time. Hence, we only measured a duplicate. So for the dry weight measurement, as per the Gantt chart, the dry weight and the HPLC conducted in symbiosis. For the dry cell weight, measure 1 mil of sample into 2 pre-weighed out Eppendorfs. And note that the weight of these Eppendorfs. Spin these down for 8 minutes at 10,000 RPM. Collect the sample and remove the supernatants into 2 separate Eppendorfs. This will be used for the HPLC. Add 2 by 1 mil of deionized H2O to the pelleted Eppendorfs. This will wash them and then vortex to mix well. Spin down again at the same parameters. Remove the water without disturbing the pellet. Now, if the water looked hazy, repeat step 4. Remove as much water as possible without disturbing the pellet. We dry the pellet overnight and weigh the sample again at room temperature. Note the increase in weight. So finally, the HPLC. At step 3 of the dry cell weight, we collected supernatants in the 2 separate Eppendorfs. This is then used to conduct our HPLC analysis. Using a benchtop syringe and filtration, collect the supernatant in a vial for HPLC. Complete the HPLC and graph the standard curve on lactose reading. And then I'm going to pass you over to David to results in discussion.
Thanks, Connor. Moving on to the results and discussion of the 5 analytical tests, these being optical density measurement, dry cell weight, cell count, oxygen concentration, base addition, and the HPLC tests. Firstly, so just move on there. Thank you. Firstly, we'll go on to optical density. So the average optical density results show an increase in OD over time. As seen in the first graph above, the initial data points from day 1 correspond to the pre-lag phase. Our lactobacillus strain is likely acclimating to the fermentation conditions. This is characterized by the slow increase in cell density. Day 2 data points at 24 hours, we begin to see an increase in the OD readings, highlighting the transition from pre-lag to lag phase. Ideally, starting the fermentation at the bacterium strain's optimal temperature of 30 to 40 degrees Celsius will cut down the lag phase, producing an improved kinetic graph. Day 3 data displays an increase in the OD readings and our peak OD concentration. At this point, the bacterium is entering the log phase, meaning that it's adapted to the new environment and it's utilizing its metabolic pathways to take up lactose and increase cell biomass. This is further confirmed by our bottom graph. If you look at it, where we have the average dry cell weight and cells per mil versus time. So, as we can see, the cell numbers increased as time went on. On day 1, we see stable concentrations of dry cell weight and cells per mil. This corresponds to the previously discussed pre-lag phase. On day 2, the data, which is T7 on the x-axis, is where we begin to see an increase in both parameters. Ideally, if leaving the fermentation for another day would give us an improved understanding of the growth rate, allowing the lactobacillus strain to provide data on the log phase. Moving on to dissolved oxygen. So stable oxygen levels were initially seen, corresponding to the lag phase. This data indicates that there is relatively low oxygen demand, meaning the cells are still adapting to their environment. And while the microorganisms are undergoing the lag phase, they're undergoing preparatory adjustments to their environment, showing stable oxygen consumption as they acclimate. This is known as the pre-lag phase. Upon entering the lag phase around T24, there's a notable drop in oxygen concentration, mirroring the exponential phase in the cell count observed at T24 on the bottom cells per mil graph. This synchronization underscores the direct relationship between oxygen demand and microbial proliferation, emphasizing the critical role of oxygen monitoring in fine-tuning fermentation processes for optimal outcomes. Next slide. So, moving on to base addition. So the bioreactor data displays the profile of 3 molar sodium hydroxide addition as the fermentation proceeded. As the lactobacillus strain metabolizes, it increased levels of lactic acid as it breaks down lactose. To keep the fermentation at an ideal pH of 6, the pH probe inserted into the bioreactor continuously took pH readings and added base via pump 2 to counteract the acid production. Initially, we see negligible base addition due to the pre-log phase and the bacterium producing minimal amounts of lactic acid. As time increases, we see an increase in base addition, indicating the drop in lactose concentration and increase in lactic acid, causing the corresponding drop in pH, which the pH probe feeds back to the base pump. The graph begins to level off at 1,000 minutes. This corresponds to where the fermentation was stopped and is not to be confused with the stationary phase. Finally, HPLC. So the first graph portrays our lactose standard curve. This was composed of readings from samples with known lactose concentration. Lactose interacts with the stationary phase and mobile phase and is retained for a longer amount of time, leading to a retention time of roughly 11.5 minutes. As the retention time for lactose remains constant, we could determine which peak and peak area, which is area for millivolts per second, on the resulting chromatograph was the lactose component. Using this information and the equation of the standard curve, we could determine the lactose concentration in our samples. We could begin to see a drop in the lactose concentration as time progresses. This indicates that the cells have begun to become accustomed to the fermentation conditions and began to use lactose in their metabolic pathways. This is mirrored by the increase in cells per mil on the graph shown previously. Ideally, by increasing the fermentation time, we would see a sharp drop in the lactose concentration as the cells begin to utilize it and enter the log phase.
And finally, in conclusion, our overall findings were successful in that the results showed that the Lactobacillus rhamnosus entered the log phase and consumed the lactose and produced lactic acid as per the results section. However, if we were to repeat this experiment, these are the few adjustments we would make. Increasing the bioreactor's working volume would enable us to withdraw larger hourly samples and conduct quadruplicates to improve graph results and its corresponding error bars. Although Lactobacillus rhamnosus has an optimal temperature of 30 to 40 degrees Celsius, they show a prolonged but effective lactose consumption at 20 degrees Celsius. Obtaining samples for an additional 48 hours could confirm our findings, indicating that the bacteria have just entered the log phase. Thank you for listening.